Hello and welcome to part B of my series of videos called Join the Dots. In these videos I take dot to dots, or join the dots as they are known, and using computer vision I automate the drawing process. So as a human you would read the numbers, and using a pen or pencil you would join up the dots in the sequence of the numbers. But I am using a computer vision algorithm to do it because it's an interesting challenge. It's a bit pointless, but it's very interesting to apply techniques to solve problems like this, and it's very I find people have responded very well to it so far because it's very I don't know, there's something about it which is fun. So in the previous video I showed that with dot to dots from my magazine I could recognize the dots and interpret the digits to form numbers, and then using these numbers and the dots we could automatically group things together and then draw a line to fulfill the sequence from dot to dot. So this time I wanted to apply this technique but on video, and at the end of the last video, and I'll show you here again, the quality of the video isn't good enough that the algorithm would work with the lower resolution of the video and also the blurring from moving the camera around. So essentially the algorithm in how I approached it before is not good enough, it's not robust enough for video. So I decided to sort of start again in a sense and come up with a methodology which would allow me to apply the dot to dot representation from one high quality image and apply it to a video so that you could still see an updated version of the representation as the camera moves around and looks at the dot to dot from a different angle. And broadly speaking I've been successful, and in the remainder of this movie I will show you how I went about approaching it and then some results. So once again I hope you enjoy, and if you like the video please subscribe and like it on YouTube. So just as a recap, what we want to do is take our high resolution image, for example the one on the left, take the line-to-line representation and apply it to a low resolution video which is moving around and which has sort of blurring artifacts and other problems, and we need to be able to do this in a quick and robust way. Okay, so how do we do that? Well, what we need to be able to do is recognize points in one image, for example our high resolution image, and recognize those same points in another image. For example, this image on the right, which is taken from a different angle, and in terms of the guitar is lower resolution because it's further away. So we need to be able to uniquely identify points in both images and find the correspondence, i.e. Join them up. So how do we recognize these points in different images? Well, within the field of computer vision there are a number of algorithms that do this. SIFT and SURF are examples of this, where if you take, for example, this cereal box on the left hand side, you can recognize points within that image which are robust to rotation and translation and to scale, despite these sort of transformations on the image as they have done here on the right hand side, and the matching points have been joined up with lines. Now SIFT and SURF are very effective algorithms, but they're really for images that have more texture than these dot-to-dot images. And because they are powerful, they also tend to be quite slow, and they are also patented. So if you're going to incorporate these in your own scripts and potentially sell them, then you can't use them. So there's a limit to how applicable they can be. So I needed something different, but which had that scale and variance, so it doesn't matter how big the object is that you're looking at, and also rotation invariance, so you could rotate your object and still have those same points, same salient points recognized. And I realized my problem was very similar to that of for looking at stars. So the night sky moves, it rotates, and also the equipment used to look at the night sky differs. You have different magnifications of telescope. So what I wanted was something very similar to how you recognize constellations in the night sky. So I had to think, and I worked out how they do this. What they do is that if you have your night sky, they join up the nearest neighbors of each of the stars and then measure the angles between the lines that join up these nearest neighbors. So, for example, if we move around the image, we take individual stars, we connect it to the nearest 5 or 6 neighbors, and then we will measure the angles between these lines that appear. And once you know where you are looking, so if you have your longitude and latitude, then it's very easy to join up the right stars to form the constellations. In this case, the Big Dipper. So how can we apply that in our images? Well, we have dots, just like the stars, and we have some clutter. Now, in the software Fiji ImageJ, there's a plugin called the Find Maxima plugin. And this is a great way of finding bright spots on an image. Now, we're not looking for bright spots, we're looking for dark spots. But the same principle applies, we just invert our image first. So this algorithm has multiple steps, and the first is to invert the image and then to find the local maxima. So these are the sort of brightest or darkest areas on a very sort of local level. Now, if you do this to an image, you'll notice you get lots of points emerging. This is because in a 3x3 neighborhood, you're going to find across a whole image many local maxima. And so what the Find Maxima finding algorithm in Fiji does is it prunes away these sort of sub-maxima and leaves you with just the brightest points, or in our case, the darkest points. And then you can find the thresholded area within a tolerance corresponding to each of these maxima, and then you're left with an image, a thresholded binary image, where you're just left with the sort of darkest areas in each area. Now you can see there are some numbers still remaining, so what we do is we isolate each of these regions and then we just filter them to say, are they circular or not? And then once you do that, you are mostly left with just the dots in our image. And this approach is invariant to scale and rotation, so it's perfect for what we want to do. So if you zoomed in on this image or you zoomed out, you'd still find the dots, and also even if you rotated the image. Now, we couldn't use Fiji ImageJ as part of our pipeline because that would be very slow and have to go in and out of the software. So I took a Python implementation of the algorithm that I wrote and I sped it up using Cython to make a very quick algorithm. So Cython allows you to compile components of your Python code in C, which speeds it up dramatically. Okay, so once we'd found the dots in our image, once we'd detected our features of interest, we then wanted to describe them. So in the case of the stars, this was done by joining up the stars to their nearest neighbors and then calculating the angles between them. So this would work if you rotated the image or zoomed in and out. The angles don't change, they're invariant to scale and to rotation. So once we have the maxima, we just find which are the nearest to each point, and then we draw a line and then we measure the angles. And what this does is it provides us with a vector for each star, giving us the angles between that star and its nearest neighbors. So here are 3 examples here for 6 neighbors. Now, just as a recap, because these are angles and you're basically going around a complete circle, each vector will sum to 360 degrees, and each detected dot has a vector which describes it. This information can then be used to uniquely identify each dot with respect to its neighbors without needing to know the number, the digit. Essentially, it's a fingerprint which allows you to identify each dot within its neighborhood. And this is much quicker and robust than the approach that we used in the previous video, where we actually read and tried to understand the dots. In blurry or low resolution video, it's much easier just to find these dots using an algorithm like the find maxima algorithm than it is to explicitly identify and recognize each digit and try and group it to a dot. So we're basically learning to recognize parts of our image without having to sort of do the very hard work of reading each of the digits. So once we have our features, our points, identified in each image, and we have a vector describing each one, what we want to do is match these vectors between our two images. So we call this process feature matching, and basically means just finding the same or similar list of values corresponding to a dot in each image, and hopefully the same dot in the context of the overall image. So you can see that these two sets of vectors are identical, meaning that we have found the same point in image 1 as exists in image 2. If we were to apply this visualization to the images below, then we can see we join up the dots with the same local neighborhood, which also happens to correspond to the same dot and therefore the same number. But all we've done is found the dots and looked at the angles between them to identify them. So here's a worked example. So if we take our violin here, where we've applied our high resolution classification algorithm, and we've got our line representation on it, and what I've done here is I've visualized the violin and also the features that have been identified as black dots, and then above to the right we've got the same low resolution image corresponding to the video frame, and you can see that a certain number of features have also been identified, also shown with black dots. And then what we want to do is feature matching, so we want to identify which points are the same between the two images. So that's what we've done here, either labeling them in blue in the main image or orange in the low resolution image. So these correspond to matching pairs, and then I'm just superimposed lines to show which dot corresponds to which other dot in the corresponding image. And you can see towards the top of the violin there's a line which connects. Actually, I don't think it is a violin, is it? It's a viola. Anyway, so you can see at the top of the viola there's one stray correspondence, which is probably a mistake that the algorithm makes, but as long as the bulk of the correspondence are correct, we're about to calculate the transformation. So given that we have a line representation on our high quality image and we know the corresponding points, we can then project our line representation onto our low resolution video image using the correspondence as a means of scaling and positioning the line representation onto this image. And then going through the video frames, we can update each frame the position of the line representation, but I'll show you more examples later. Now, when I say transformation, there are many forms of transformation. For example, there's a similarity transform where you would just scale and rotate your in our case a line representation to make it fit. Or there's a more complicated affine transformation, which includes rotation and scaling, but also shear. But what it does is it maintains parallel lines in an image. Now, in a sort of perfect optical environment, that would be sufficient for our example, because we have a flat image and we're just moving it around in space. So that, generally speaking, an affine transform would be sufficient for that. But because our system isn't perfect, we have certain optics that have a certain depth of field, we actually can't use an affine transformation. This wouldn't be sufficient to account for all of the sort of optical effects that we see. So we use an even more complex but flexible transform called the homogeneous transform. And this means that we can account for transformations in our line representation, which include shear and scaling in multiple ways. So we can go from a box to any other shape which would represent our plane being positioned anywhere in a 3D space, and the sort of optical artifacts of our lens and the depth of field as well being accounted for. Now, this process of calculating the transform involves machine learning, and what we are doing is learning the parameters of a transformation matrix, which uses things like singular value decomposition, which involves forming a number of linear equations and performing a decomposition to calculate what those parameters are. So the more correspondence we have, the more calculations we can form, and the more reliable our estimate should be, as long as they're in agreement. And what I'll do is I'll put a link in the description below to more details on this, because it's a big subject to cover in any detail. But what I did is I used the OpenCV library for finding a homography, and that allowed me to calculate this homogeneous transformation, which allowed me, given the correspondence, the matching correspondence, allowed me to transform my line representation into the space of our video image in each frame. Okay, so here is our comparison. Remember, on the left we had our original attempt using the high resolution algorithm, and we found that it performed very poorly. And on the right we've got our new algorithm, which isn't perfect and sometimes it does fail, but it is a far superior attempt at the augmented reality solution than our previous one. And it also works a number of frames per second, so depending on your laptop you should be able to get more than 4 or 5 frames per second. And that's on code that's been somewhat optimized but not fully optimized, so you could imagine this running on a mobile phone for existence. So that's the two sort of chick example, but we also have, for example, some better examples. For example, the viola, which is working very well. This girl playing the recorder, a little bit shaky but pretty good. And also the Easter egg, which given the number of dots and the level of zoom, works very well. So the focus is important. It has to be able to see the dots, but all things considered, it's working pretty well. And I could actually see this being as part of a sort of mobile phone app, which would allow you to visualize these dot-to-dots, which is a good success. So there we have it. Please follow me on these different forms of social media. I want to specifically post videos about the dot-to-dots that I've created and visualized on Instagram, and also for the code itself, please follow me on GitHub, and I'm always doing updates about my scientific work and also this project on Twitter, so I'd be much obliged if you could follow me on that. And in terms of the future, there is going to be a part C to this video where I actually show you how you can make your own dot-to-dots. So you will provide a line drawing, and then the algorithm will convert that into a form which will allow you to present it as a dot-to-dot, either for you to draw on or maybe a child of yours. Once again, thank you for following me and watching my video to the end, and I hope to provide more content for you in the future. Thank you.